How Discord reduced their WebSocket traffic by 40%. This is an interesting blog post coming right out of Discord's official blog, which states a few things about the optimizations Discord as a platform made to reduce WebSocket traffic. So let's try to understand this blog post in a little bit of depth, how all of this is working, what optimizations did they do, and what you as a developer can learn from it. So all of us know Discord, so I'll just skip that part where you don't know what Discord as an application is. So let's start with the blog post that says, like, over the last 6 months we embarked on a quest to support this endeavor, working to reduce the amount of bandwidth our clients use, especially on iOS and Android, hoping that this would decrease in bandwidth usage would lead to more responsive experience, right? So there are many things that happens when your systems become more performant, your cost reduces, your experience improves. So it's always a good idea, right? So when your client connects to Discord, it receives the real-time updates about what's happening through a service that we call the gateway. Since late 2017, the client's gateway connection has been compressed using zlib, which makes the messages anywhere from 2 to 10 times smaller. So this gateway, I am assuming, works and operates on WebSockets, which, by the way, like, makes sense. If your whole application in general is real time, then you have to keep it that way. What they do is that they compress the messages. So we can also check that, right? So if I open Discord on my web browser, I would be able to check that, go to the WebSockets tab, and you can see that I am already connected to a WebSocket that has this URL of encoding JSON version 9 compressed zlib stream, right? So all of that is already here, right? So let's see. So if you go into this, you can see that the client is sending the messages in JSON, but the server is responding in a compressed message format. So if I expand this a little bit, so let's see, if I copy this as base64, I mean, if you try to decode this by copying it and seeing like copy as hex or UTF-8, and if you write a function, you'll probably get some data on like how Discord is sending what these messages are, but they are most likely zlib stream encryption. So you have the idea, and you can also see like gateway.discord.gg is the domain at which it's connecting, right? So it's behind Cloudflare, obviously, but I am assuming that these servers, the WebSocket servers, are raw, like they're handled by Discord itself. So anyway, when your client connects to Discord, it receives a real-time update about what's happening through a service called Gateway. So they apply a compression, which makes it 2 to 10 times smaller. Since then, Z standard, originally released in 2015, has gained enough traction to become a viable replacement for zlib. So Z standard, or Z standard, how people call it, it's compression algorithm. Basically, what it does is that what you have to understand is that there are multiple compression algorithms, right? So if I fire up a TL raw real quick and open a new page, so what you have is compression algorithms. One of them is zlib, one of them is Z standard, which is relatively newer. gzip is one, brotli is one. For example, you would have seen like brotli is a very common thing, and there are a couple of more, right, which are like good enough. So how compression in general works is, if I talk about that a little bit, let's say you have a file, which, just giving you a very basic example, which has 100 A's, right, up to 100. So if you want to compress this file, so this file would be of 100 bytes, right, because 1 A would be 1 byte. So now if you want to compress this file, what you can do, I mean, just as a manual compression, is that you can write something like A cross 100, right? Now, of course, like if you're actually storing this data itself, how you would represent that, that's a completely different thing. But just to make it simplified, for example, in your dictionary, let's say in the file you're compressing, it only contains A and B, you can write something like this. So what this becomes is 1, 2, 3, 4, 5 bytes. So you have effectively compressed something from 100 bytes to 5 bytes without losing the data, right? So this is a lossless compression where your data is retained. Lossless compression is extremely important in files and messages, like for example what you are sending. However, if you have images, for example, as a thing, then over there lossy compression sometimes is also fine, right? Because with images, the thing is that even if you lose some data about the pixels, it's okay, because the image itself is like, it's constructed as a whole, right? So you would still be able to make sense of it. But lossless compression is what you need, I mean, almost all the times with files and messages and all of that, so you don't lose the data, right? So all of these like Z standard, gzip, brotli, they do support like lossless compression. So Z standard is algorithm that's developed by Facebook. I think it's still maintained by Facebook, and it's extremely powerful, right? So if you look at, so this is a dictionary thing, we'll discuss about this, but if you look at this table, which like is sort of like a benchmark for Z standard, so you see that on a generic, they use some common zip file or something. On that, Z standard does a 2.887 ratio of compression, zlib is 2.7, brotli is 2.7 again, 7, 4.3, zlib is slightly better than Brotli, then Z standard is better in fast mode, and so on. Like it's slightly worse in fast mode, and then so on, right? So yeah, not only it's better, but it's also fast, right? It's compressing far faster than zlib or decompressing as well. We in fact also use Z standard internally when transmitting data for, live streaming, right? So the Fermion live streaming infrastructure which is built, this works on Z standard, the playback and the live streaming. So to give you an example of that, this is one of the live streams that has happened on, one of the platforms that is powered by CodeDam. And if you go into this fetch tab, you will see that we also use Z standard as an encryption way for compressing the data, and it really is good, right? So Discord says we attempted to use Z standard in the past, but at the time the benefits weren't worth the cost. Testing in 2019 was desktop only and used too much RAM. So they wanted to give it another try because it's been 5 years now. And armed with this knowledge, we put on our lab coats, slapped our goggles, and started experimenting. We opted to do a dark launch of plain Z standard. The plan was to compress a small percentage of production traffic, both with zlib and Z standard, collect a bunch of metrics, and then discard the Z standard data. This allowed us to experiment with Z standard quickly to compare its result against zlib. Without this experiment, we would have to add Z standard support for our clients, desktop, iOS, all of that, which would require about a month's lead time before we can fully determine the effects of the compression. Okay, so what they did basically is that how Discord is obviously likely working is that you have this Discord server, right? And then you have this client, right? Now, because this architecture is not as simple as just connecting directly to Discord server, but still you would have a load balancer or something like that in between. But because this is WebSockets, it's relatively simpler to understand that it's a two-way communication. So what happens is that whenever the server is sending some data to client, what it's doing on the server side is that it's taking that data and converting that into Z standard plus zlib. So it's doing both compressions, and then it's discarding the Z standard one, right? Because your client still only understands how to decompress zlib. In order to understand Z standard, they'll have to ship a lot of the code on the client side also, because the decryption has to be done on the client side. So yeah, they got their experiment set up, deployed it on our gateway cluster. We set the dashboard to see how Z standard performed. We flipped the switch and started sending a teeny bit of traffic through the dark launch code, and the initial results appeared to be underwhelming. Z standard was performing worse than zlib was. Okay, so you see over here, so this is the Z standard compression ratio, about 12.26 for user guild setting update, and over here it's 13.95. So zlib is better. To compare the performance of these two compression algorithms, we use their compression ratio. The compression ratio is measured, that's fine, we know what compression ratio is. So it's basically is if you're, like I said, if you are creating 100 bytes of code and then you are, reducing it to 5 bytes, so your compression in this case would be 100 by 5, which is 20 times, right? So you have compressed your data 20 times. Looking at the images above, which measure the compression ratio for various dispatch types, with zlib, user guild setting updates has a compression ratio of 13.95, while Z standard has a compression ratio of 12.26. So in their initial test, they figured out that Z standard was actually bad, right? So what's going on here? Because it's not really bad, because if you look at the metrics, for example, over here, the benchmark, it clearly works better than zlib, both in terms of compression and in terms of speed. So what's going on? Well, for their specific use case, what they want to do is use streaming Z standard. It turns out that one of the key differences between zlib and our Z standard implementations was that zlib was using the streaming compression while Z standard wasn't. As mentioned previously, most of our payloads are comparatively small, only a few hundred bytes at most, which doesn't give Z standard much historical context to work with to further optimize how to compress future payloads. So there is one concept in Z standard, which is the concept of having a dictionary, right? So if you look at this section, for example, which Facebook officially lists, the case for small data compression. The smaller amount of data to compress, the more difficult it is to compress, which is interesting because see, if you have just a very small amount of data, the problem that happens with that is that common to all compression algorithms is that they learn from past data how to compress future data, right? But at the beginning of a new data set, there is no past to build upon. So as far as I understand, I feel like the more data you have, the more patterns the algorithm, the compression algorithm can recognize, the more time it can spend on that file to figure out which chunk of data should go where in the new compressed version. So the bigger files are usually better in terms of compressing. To solve this situation, Z standard offers a training mode, which can be used to tune the algorithm for a selected type of data. Training Z standard is achieved by providing it with a few samples, one file per sample. The result of this training is stored in a file called dictionary, which must be loaded before the compression and decompression. Using this dictionary, the compression ratio achievable on small data improves dramatically, right? So you can see that the compression ratio without a dictionary is 2.8 for some data set, and with dictionary it jumps to 9.9, almost 10 times, right? Like not 10 times, but almost like 10x. Compression speed also increases and decompression speed also increases a lot. Training works if there is some correlation in a family of small data samples. The more data specific a dictionary is, the more efficient it is. There is no universal dictionary, obviously. Hence, deploying one dictionary type per type of data would provide the greatest benefits. Dictionary gains are mostly effective in the first few kilobytes. Then the compression algorithm will gradually use previously decoded content to better compress the rest of the file, right? So what they're basically saying is that if you have a very small set of data, like Discord has, for example, it makes a lot of sense for you to compress the data and decompress the data with a dictionary, which includes information about what sort of data you are going to compress and decompress. So as mentioned previously, most of our payloads are comparatively very small. With streaming compression, the zlib stream is spun up when the connection is opened and exists until the WebSocket is closed. Instead of having to start fresh for every WebSocket message, zlib can draw on its knowledge of previously compressed data to inform its decision about how to process fresh data. This ultimately leads to smaller payload sizes. So what they're doing effectively is that for this whole thing, for this whole journey, like since the time I have joined this, opened this website, there has been on the Discord side, there has been a service from zlib that has been opened, and it just keeps on living until the WebSocket connection dies, right? So it is continuously building on that history of the messages with the server, which the server is sending to the client and so on. So it gets more and more efficient, right? The question then became that could we get Z-Standard to do this? The answer to that was sort of. Our gateway service is written in Elixir, and while Z-Standard supports streaming compression, the various Z-Standard bindings for Elixir and Erlang we looked at did not. Okay, so we ultimately settled on using EZ-Standard as it has dictionary support. More on that later. While it didn't support streaming at the time, in the spirit of open source, we forked it and added support for streaming, which we later contributed back to upstream, right? So this contribution came from Discord directly, which they have also mentioned in their blog post. And this engineer, like you can see, also works at Discord. So that's great, right? You are using something and you are contributing it back to the actual project, which sounds good. Now, they repeated the dark launch experiment again, but with Z-Standard streaming, and got the following results. Now you can see that zlib is far behind in Z-Standard in terms of compression, right? Z-Standard streaming is much better than both the approaches. So not only that, this trend held true for most other dispatches, and Z-Standard streaming significantly outperforms zlib in both time to compress and compression ratio. What this basically means is that you will have more time, CPU time, for doing other things because the algorithm which you chose is much more effective. Looking once again, the compression time per byte of data is significantly lower for Z-Standard streaming than zlib, so that's great. So pushing further, let's see what else did they do. While our initial experimentation proved that Z-Standard streaming outperforms zlib, the remaining question was that how far we can push this. Our initial experiments used the default settings, and we wanted to know how high we can push our compression ratio by playing around with the compression settings. So how far did we get? So Z-Standard is a highly configurable and enables us to tweak various compression parameters. We focused on our effects on 3 parameters we thought would have the biggest impact: chain log, hash log, and window log. These parameters offer trade-offs between compression speed, memory usage, and compression ratio. For example, increasing the value of chain log generally improves the compression ratio, but at the cost of increasing memory usage and compression time. We also want to ensure that with the settings we decide on, the compression context would still fit in the memory on the host. While it's simple to add more hosts to soak up the extra memory usage, extra hosts cost money and at some point provide diminishing returns on the gains. Yeah, of course. So it's a balance between, the data you are transmitting over internet versus the compute that is required to compress that data, right? So at some point, like he says, it would outperform the gains. So these compression levels, chain log and hash log of 16. So Z-Standard, I wasn't aware like there are 2 more parameters. But what I have seen is that Z-Standard offers like a compression level up to I think 20 or something. I don't remember the exact number. If you go over here, level, yeah, up to 22. So what happens with levels, I mean personally what I've seen is beyond like 15 or even 16 is that the compression time increases a lot, but the compression amount is like roughly the same, right? So you will still get the same sort of payload at the end. We wanted to investigate if we could take advantage of Z-Standard's dictionary to support compressed data even further. By preceding Z-Standard with some information, it can more efficiently compress the first few kilobytes of data, which is what we talked about in the dictionary manner. However, doing this adds additional complexity as both the compressor, in this case a gateway node, and a decompressor, a Discord client, need to have the same copy of dictionary to communicate with each other successfully. To generate dictionary to use, we needed data and lots of it. Z-Standard has a built-in way to generate dictionaries with train flag from a sample data, so we just had to collect a whole bunch of samples. Notably, the gateway supports 2 encoding methods for payloads, JSON and ETF. Since dictionaries contains portions of training data and we'd have to ship dictionaries to our clients, we needed to ensure that the samples we would payload generate of the dictionaries were free from any personally identifiable user data. Again, like a very important point and something you can easily miss in the technical discussion, that the dictionaries which you are creating could have like some level of personally identifiable data. So they collected over 120,000 messages, split them, anonymized them, and generated the dictionaries. Once the dictionaries were built, we could use our gathered data to quickly evaluate and reiterate on the efficacy without needing to deploy our gateway cluster. The first payload we tried compressing was Ready. As one of the first and largest payloads sent to the user, Ready contains most of the information about connecting users, such as guild membership, settings, and read states. We compressed a single Ready payload of about 2.5 million bytes down to 300,000 bytes, using the default Z standard settings which established a baseline. Utilizing the dictionary we just trained, the same payload was compressed down to a gain of about 600 bytes, which is, given that you have to deploy this whole dictionary infrastructure, then ship the dictionaries also, seems like not a huge gain. Initially, these results seems discouraging, but we tried compressing a smaller payload called typing start, sent to the client so that we can show that this person is typing notification. In this situation, a 636 payload compressed down to 466 without the dictionary and 187 with the dictionary. So this is where I think more gains are in terms of like percentage of the message, right? We saw much better results with our dictionaries against smaller payloads simply due to how Z standard operates. This is what exactly the documentation for Z standard also says. If you are going for small data compression, the gains are immense. The compression ratio is immense, and in the documentation you can see that training works. Dictionary gains are mostly effective in the first few kilobytes, right? So if you are sending a message which is huge anyway, like 2.5 million bytes, then you would not get a lot of gains, like it's evident from here. But for smaller messages, it's great. Satisfied with these findings, we deployed a dictionary support to our gateway cluster and started experimenting with it. Utilizing the dark launch framework, we compared Z standard to Z standard with dictionaries. Our production testing yield the following results. If dictionary is present, then the compression ratio is 6.63. Without that, it's slightly smaller with 6.4. We specifically looked at the Ready payload size as it's one of the first messages sent and would be most likely to be benefit from a dictionary. As shown in the table, compression gains were minimal for Ready, so we looked for the results for more dispatch types, hoping dictionaries would give more of an edge for smaller payloads. Unfortunately, the results were a bit mixed. For example, looking at the message create payload size, which we have been comparing throughout this test, we can see the dictionary actually made things worse. Interesting. So using dictionary in general with message create as a graph, plotting it on a graph, it made it slightly worse. Ultimately, we decided not to continue with our dictionary experiments. The slightly improved compression of dictionaries that they would provide was outweighed by the additional complexity. So this makes a lot of sense because you can see like it doesn't, in terms of like as a net experience, it doesn't improve that. So it's not worth to include dictionaries. Then they did something else also, buffer upgrading. Finally, we explored an increasing Z standard buffers during off-peak hours. Discord's traffic follows a diurnal pattern, and the memory we needed to handle peak demand is significantly more than what's needed during the rest of the day. On the surface, autoscaling our gateway cluster would prevent us from wasting compute during off-peak hours. However, due to the nature of gateway connections being long-lived, traditional autoscaling methods don't work well for our workload. This is exactly one of the biggest problems with WebSockets. The reason they are saying like things don't work is because this is not an HTTP based thing, this is a WebSocket thing. As such, we have a lot of extra memory and compute during off-peak hours. Having all this extra compute laying around raise the question, could we take advantage of these resources to offer greater compression? To figure this out, we built a feedback loop within the gateway cluster. This loop would run on each gateway node and monitor the memory usage by the clients connected to it. It would then determine a percentage of new connecting clients that should have their Z standard buffer upgraded. An upgraded buffer increases the window log, hash log, and chain log values by 1, and since these parameters are expressed as power of 2, increasing these values by 1 will roughly double the amount of memory usage the buffer uses. So what they are doing basically is that at night, when there is no, night as in like there is no night as such for Discord, but when their peak hours are not there, they would use the extra compute they have to offer better level of compression. After doing a bit of digging, we discovered that one of the primary issues that was causing the feedback loop to behave suboptimally was memory fragmentation. The feedback loop looked at the real system memory usage, but Beam was allocating significantly more memory from the system than it was needed to handle I think I missed a paragraph somewhere. Yeah, after deploying it and letting the loop run it for a bit, the results weren't as good as we initially hoped, okay? As illustrated by the graph below, over a 24-hour period, our gateway nodes had relatively low upgrade ratio, up to 30%, and was significantly less than what we anticipated. So long story short, they did not go forward with this approach. After messing around with the allocator settings for a bit, we decided to revert the feedback loop. So then finally, while the original plan was to only consider Z standard for mobile users, the bandwidth improvements were significant enough for us to ship it to desktop users as well. So this just found Z standard implementations within the respective platforms, but for iOS they wrote their own bindings. This was a risky change with the potential to render Discord completely unusable if things were to go wrong, so the rollout was gated behind an experiment. This experiment served three purposes: allowing the quick rollback of these changes if things were to go wrong, validate the results we saw in the lab, and then enable us to gauge if this change was negatively affecting any baseline metrics. Because if you're rolling this out, what you also have to be careful about is that the client doesn't get slow because of the compression and decompression, right? Because of the decompression mostly. Over the course of few months, we were able to successfully roll out Z standard to all of our users on our platform. I don't understand then why do I get this payload where it says compress zlib stream on the web browser? I'm not sure. Like I've not checked these messages, but these might be Z standard messages. But then it seems a little weird that why they are using zlib stream in the WebSocket URL, right? So that's a little bit weird. So another thing they did was, it's not directly related to Z standard, but the metrics that guided us during the dark launch phase of this project revealed a surprising behavior. Looking at this actual size of dispatches that were sent to the client, passive update V1 stood out. This dispatch consisted of over 30% of our gateway traffic, while the actual number of dispatches sent were comparatively small, around 2%. So what is this passive session exactly? We employ passive sessions to avoid sending most messages that a server generates to clients that may not even open the server. For example, a Discord server could be very active, sending thousands of messages per minute, but if a user isn't actually reading those messages, it doesn't make sense to send them and waste their bandwidth, which is true. Once you tab into the server, a passive session will be upgraded into a normal session and then receive the full fire hose of dispatches from that guild. Makes a lot of sense, right? However, passive sessions still need to be periodically sent limited amount of information, which is the purpose of passive update V1. Diving into periodically, all passive sessions will receive an update with a list of channels, members in voice, so your client can still be kept in sync with server. Okay, diving into the actual contents of one of these updates, we would send all of the channels, members, or members in voice, even if only single element is changed. Passive sessions were implemented as a means to scale Discord servers to hundreds of thousands of users, and it worked well at the time. So that's interesting. For example, right now I'm not using Discord, it's in the background tab, but they still are sending some level of passive updates, right? Every once in a while to let the client, in this case this browser tab, know that things are getting changed. So more unread messages are there, somebody has joined a voice channel and so on. However, as we continue to scale, sending these snapshots, which consist of mostly redundant data, was no longer sufficient. To fix this, we introduced a new dispatch that only sells the delta of what has changed since the last update. This dispatch, aptly named passive update V2, significantly reduced the overall bandwidth from 35% of the gateway's bandwidth to 5%. So 35% of the bandwidth was going on passive updates, which is like a huge number. And reducing it to 5% is like a lot of savings in bandwidth. Through the combined effects of passive session V2 and Z standard, we were able to reduce the gateway bandwidth used by clients by almost 40%. That's a lot of data, because if you look at Discord, it's probably doing petabytes of data a month, right? So this 40% saving would obviously correspond to a lot of saving in cost also. This chart shows the relative outgoing bandwidth of gateway cluster from January 1st, 2024 to August, and then this data drops when Z standard was shipped. So this is likely gradually shipped, and then passive session V2 is also shipped, so it brought it a little bit more down from the actual peak. So very interesting blog post. You can see, like, at scale, when you are trying to solve certain things get a lot interesting compared to like when you're building your basic to-do application or chat app. So yeah, that's basically it for this video. Let me know what you think in the comments about this infrastructure, this architecture decision. Are you using Z standard or any compression in your own stack by choice? If yes, let me know in the comments. That's all for this one. I will see you in the next video very soon.